All right, new section. In this section 5.5, we learn a technique called U-Substitution. U-Substitution may be the most important technique that you learn in this entire class. Definitely one of my favorite techniques that you learn in this class. And it falls into a new category. I call it advanced methods of integration. And these are just subcategories that I'm kind of making up, so there's no real significance there. But for me, it helps to think about the class in kind of different chunks. And I think you're now entering a different chunk of this class. We still have the same goal, right? Our main purpose in this class is the same. We're trying to evaluate integrals, be they indefinite integrals like you see here, or definite integrals. And the justification for doing these in the first place, we'll see at the very end of this class when we get into some applications. But maybe you just trust me that evaluating integrals is super duper important. And in the case of definite integrals, we saw two different ways to evaluate these definite integrals. A really hard way, namely a limit of sums, which is the first way we did these guys, and then a much easier way, which is using antiderivatives. And maybe you believe me, or you're guessing, or you can tell that the antiderivative method is going to be used a lot more prominently in the second half of this class than the limit of sums method, which was really just supposed to give you some intuition for what you're doing. So if this antiderivative method is going to be used prominently in the second half of this class, we better get really, really good at antiderivatives. And frankly, when I talk about advanced methods of integration, it's really just that, learning how to find antiderivatives for more challenging functions. Because maybe you've noticed that the things that I've asked you to find antiderivatives of have been chosen very, very carefully. Right? In Calculus 1, you learned how to take derivatives of all sorts of functions, of really complex functions, lots of different rules and stuff. And whenever we've done antiderivatives, the questions have been a little bit more basic. They've kind of been one-step problems, whereas in Calculus 1, you had multiple-step problems. Oh, you use the quotient rule inside the chain rule here, and that whole thing is nested inside a product rule. Do something crazy like that. We haven't done anything like that on the antiderivative side, and it's been very intentional to not do anything like that on the antiderivative side, because in order to do that, in order to find antiderivatives of more complicated functions, we need more tools. We need what I call advanced methods. And the first and probably the most useful advanced method is what's called U-Substitution. And so to illustrate U-Substitution, imagine somebody asked you this problem. This indefinite integral here. Essentially, it's just saying find the antiderivative of this function. They're asking you the question, when you were in Calculus 1, what question could your teacher have asked you to which you would have answered this? And if you can just look at this and tell what function has this as its derivative, that's really good. Maybe you can do this specific problem without U-Substitution, but maybe when I give you example 2 or 3, we can start to see how, okay, you really do need U-Substitution, and that method will make this one easier. Have I stalled long enough? My question is, what function, when you took its derivative, gave you this as the answer? And if you want a hint, my hint would be saying chain rule to you. And maybe that's enough of a hint for you to kind of see what's going on here. You're like, let's see, chain rule. Oh, right, that's the one where there's kind of an inside function and an outside function. So I'm kind of looking for a function nested inside of another function. And what I do is I first take the derivative of the outer part, leaving the inner part completely alone. But then I'm still not done. I have to multiply that by the derivative of the inner part. Oh, right, okay, so x to the 10th here, its derivative is exactly 10x to the 9th. So if this were the answer to the derivative of the outer part, and then I just left this alone, okay, I think I can kind of see what's going on here. Let's see, maybe this is the negative cosine of x to the 10th power, and then plus a constant if you want. If you can come up with that on your own, that's really impressive. If you can't, just make sure that you can see this and justify this, right? Let's see, if somebody asked you to take the derivative of this, you'd be like, negative, ignore that. The derivative of cosine is negative sine. So the ignored negative and negative sign cancel out. And I get sine of something. But that something, I don't take the derivative of that something because I need the chain rule. I leave that something alone. So it's the sine of x to the 10th power, but then I'm not done. I still have to multiply by the derivative of that x to the 10th. That's this 10x to the 9th. The chain rule allows us to go from here to here. And what you'll see is whenever you need to undo the chain rule, you're going to use a method called U-Substitution. So the two main things you need to know for U-Substitution is first how to recognize that it's a U-Substitution problem, which won't be a big issue in this section because we're in the U-Substitution section, so that's what you'll be looking for. But generally speaking, you'll want to get to the point where I can just give you a problem and be like, figure this out, and you'll be like, this one looks like U-Substitution. So you'll want to be able to recognize the problems, and then you'll want to be able to apply the algorithm to do the U-Substitution method. And the nice thing is those both kind of involve the same steps, recognizing them and doing them. What you want to do is look at the question that you're given, the function for which you're trying to find the antiderivative, and look for a piece inside that function for which the derivative of that piece also occurs inside that function. And we'll get a little bit more into the specifics about these pieces and where they occur, but right now I just want to make the point that if you call something, I don't know, maybe the letter U, this x to the 10th, you might notice that the derivative of that U prime, also shows up here, 10x to the 9th. Right? And the fact that x to the 10th and its derivative, 10x to the 9th, both show up in this problem is my big hint that I'm going to be using the U-Substitution method. Why are you looking for a U and a U prime? Well, it sort of makes sense. If you're undoing the chain rule, in one step you left the inside function, which is what I'm calling U, alone. And then in the next step, you multiply by the derivative of that inside function. So there's that U prime. If there's a U and a U prime, you're like, oh, okay, because in one step I left it alone, and in the next step I multiplied by its derivative. Here's the formal statement of what a U-substitution is. And if it helps you, great, although I think for most people, talking through the method that you'll do will be more useful. If you have this question, which looks really hard to find the antiderivative of, you can change it into this, which maybe looks a little bit easier to find the antiderivative of, if you just change this function g of x into u. Right? So this is essentially the substitution that you're doing here, and it lets you rewrite this complicated integral as this easier looking integral. A couple of comments here. You're like, oh yeah, okay, you just changed this u into a g of x, so this turns into f of u, I got you. But note that this g prime goes away. Right? There is no g prime over on this side. Also note that this dx, which up until this point in the class has just been a symbol which has no meaning, changes into a du. So that's a little bit complicated. Let me try to justify that a little bit. This x is just telling you what your variable of integration is, which is why there's an x here and an x here. So since I changed the x into a u, what's going on now is my u is my new variable of integration, which makes sense because I'm writing my function as f of u. So it's a little bit complicated because u is both a function and the variable of integration. But by allowing it to serve both of those two purposes, we can get rid of this part over here. Confused? Let me take you through the steps and show you how the notation that we use is surprisingly well suited for this purpose. Suppose somebody asks you this question right here. The first thing to do is recognize that it's a U-substitution problem. More on that later. The second thing to do is recognize what you want to substitute u to be. And that's going to be the big challenge here. For now, just trust me that we're going to let u equal x to the 10th power. But we're going to have to spend a lot more time on how to determine what u should be equal to in a given problem. So what we want to do when you're given this problem is recognize that it's a u-sub and then figure out what u should be equal to. So I'm going to let u equal x to the 10th power. Remember, when we go through this method, we need both u and u prime. So what I'll do in my algorithm every single time I decide I'm doing a u-substitution problem is the minute I decide to let u equal x to the 10th, I'm going to figure out the derivative of u. Maybe you're comfortable with me writing that as du over dx. And this is notation that was introduced in Calculus 1 that says u, the thing we're calling the function, where x is the variable, this represents the derivative of that function with respect to that variable. Anyways, du over dx is just asking you, what's the derivative for this guy? The derivative for this guy, that's easy. That's 10x to the 9th power. So step 1, recognize that it's a u-sub problem. Step 2, decide what u should be equal to. Step 3, find the derivative of u, because you're going to end up needing to know the derivative of u up here. You with me so far? Because this is the step where things get kind of crazy. This, up until this exact moment right now, has been a symbol, a single symbol representing the derivative of this function u. It's not a fraction. I know it kind of looks like a fraction, but it's not a fraction. The du by itself has no meaning. The dx by itself has no meaning. This is not something divided by something else. This is one big symbol that represents the derivative of this thing u. But just for a moment, just to humor me, pretend this were a fraction. Right? If this were a fraction, if this were something divided by something else, then would you be okay with me saying that the top of that fraction is equal to 10x to the 9th times the bottom of that fraction, me multiplying both sides of this fraction by dx? And you're like, well, yeah, if it were a fraction, fine, but it's not a fraction. It's a single symbol representing the derivative of this thing u. That's true, but the reason this symbol was chosen as representing the derivative of this thing u is because when we do these more advanced techniques, we'll be able to treat it as though it were a fraction. If u is x to the 10th power, and we're allowed to treat fractions in this way, then maybe you can justify how du would be 10x to the 9th times dx. Why is this really useful? Because 10x to the 9th dx is something that is in my integrand here. And you're like, whoa, wait a minute. 10x to the ninth is part of your integrand. This dx is just a symbol that is kind of attached to this integral right here that doesn't really mean anything at all. It's just a symbol that's attached to this guy to let me know what my variable is. You can't treat this as though this is 10x to the ninth times dx. Well, actually I can. Right? Even though it hasn't meant anything so far, it's written in this notation so that things will work out when we get to this step. Somebody much, much smarter than me thought ahead when they chose all this different notation and chose things to work out really, really nicely for you, the student. Look, what I'm going to do here is I'm doing these substitutions. I'll be like, this integral sign is still here. The sign is still here. And then this x to the 10th, well, I just said right here, let u equal x to the 10th. So it makes sense to write sine of u. And you're like, what about this 10x to the ninth? What about this dx? Well, right here I have written that du equals 10x to the ninth dx. So instead of writing 10x to the ninth, and instead of writing dx, I can just write du. That's kind of crazy, right? The 10x to the ninth went away. Oh yeah, I was kind of expecting the g prime of x to go away according to this symbol. My variable of integration changes from dx, or changed from x to u. Instead of having a dx here, I have a du here. It all worked out so perfectly with these substitutions because of the notation, the way I choose to write this derivative, which I've been doing since Calculus 1 without even knowing what I was setting myself up for. Okay, anyways, let that all slide for a minute. We just changed this problem into this problem. This problem I could have given you a couple sections ago, right? This could have, you always wonder when you look at the homework, how sometimes the variable of integration, instead of using an x, they'll use a weird letter like an r or an s or a u. And it doesn't matter that they chose the letter u as long as it told you that your variable of integration was a u. As long as that du here, you just do everything the same. Taking this antiderivative, no problem. It's super easy. Is negative cosine of u plus c. Right? You just treat the u as though it were an x and don't worry about the fact that somebody, for some strange reason, chose a different letter in here when they asked you this question. Right? That's how you're thinking if this is a basic antiderivative to figure out. And the nice thing is this method of U-substitution changes from an advanced integration to a more basic integration by doing this substitution and this kind of cool, dare I say cool in a calculus class, way of treating derivatives and fractions make everything work out really nicely. And you're like, so my answer is the negative cosine of u plus c? No, of course not. U is something that you, y-o-u, created in this problem. Right? The original problem didn't have any u's at all in it. This is something that the student, I don't want to say you again, created. The student decided to change u's into x to the 10th power. So I shouldn't leave my answer as negative cosine of u. I should say it's the negative cosine of x to the 10th power plus c. Which is exactly what we know the answer to be because we started out with this and we could check this by using the chain rule and taking the derivative. That's kind of wild. At least I think it's kind of wild. It's a pretty interesting technique. And what I think is especially cool about it is why does this all work? And it's hard for me to even explain why it all works. I mean, there's a more formal proof in your book and you can read through it if you want. But really the way I think about this working is some genius decided upon the notation that we will use for calculus. And you've just been kind of letting it slide. Like, fine, if you want me to use this for a symbol to represent the derivative of this thing, u, I'll do that. That's fine. If you want me to always tack on these dx's at the end of these integrals, I'll do that. I mean, if it'll make you happy. If it'll convince you that I can use the agreed upon notation, I'll do it, even if I don't see the justification for using this notation in the first place. Well, here's a little bit of the justification for using this notation that somebody brilliantly chose so that we'd be able to do stuff like this when we integrate.